All right, so objective 4 is describing apical, lateral, and basal surface features of epithelia. So what's going on in the apical surfaces? Kind of sort of started talking about that. What's going on in the lateral surfaces, and what's happening at the basal surface. So first we'll start with the lateral surfaces. And the lateral surface features of epithelial tissue basically have 3 factors to keep the integrity of that tissue. Right? To keep the integrity of that tissue. Most importantly are the cell junctions. So there are certain junctions. And when I say junction, I mean an apparatus that is literally holding these 2 cells together. And that's going to be the most important thing. But there's also adhesion proteins, as well as the contours of the adjacent membranes. And when we say contours of the adjacent membrane, we talk about like interdigitation between the cells. So the cells are going to sit together like grooves, like a groove and socket appearance. So they fit together like pieces of a puzzle, and that's also going to help with the integrity. But the most important thing is going to be the cell junctions. I'm going to talk about the types of junctions. There are 4 types. The tight junctions. These are also called zona occludens. Zona occludens. That means to close off. Close off. And these junctions provide a tight seal between adjacent cells. Zona occludens. A tight seal between these 2 cells. Why? Because we don't want material to sort of seep through the sides of the cells. So you have your, let's take our simple columnar epithelia of the gastrointestinal tract. We have digestive enzymes in the gastrointestinal tract. We have acid in the stomach. We don't want that acid to seep in between the cells and get to the underlying connective tissue. So we need a tight junction to provide a seal between cell to cell. And that's your zona occludens, also called your tight junction. So this is preventing seeping or movement of any molecules in between, again, from the apex down to the basal surface of these cells. And this is going to be found way at the top of the lateral surface. Then you have your adhesive belt junctions. The adhesive belt junctions, and these are called zona adherens. That's because these are adhesive junctions or anchoring junctions. Anchoring junctions. There are going to be some proteins, right, within the plasma membrane of each cell that are going to connect to some filaments within the cell. And these are going to prevent anything from going up or down and sort of anchor everything together like a belt wrapped around the periphery of the cell. These are going to keep everything nice and steady at the same level. Not one cell moving up, down, anchoring everything together. An anchoring junction. Like a belt, like a tight belt wrapped around the periphery of the cell. Desmosomes are going to be right beneath your anchoring junctions. Again, this is the order that we find these along the lateral surface of the cell. Desmosomes are also anchoring junctions. So these act a little bit differently. You can actually see them. So desmosomes, so these were your tight junctions, providing a tight seal. These were your adhesive belt junctions, like a tight belt wrapping around the surface of the cell. These are your desmosomes. Now, desmosomes are going to have on their plasma, their cell surface, so the surface that's facing the cytoplasm, some proteins. And these proteins go all the way through the cell. You can see them connecting on either side here. They also have this interdigitation in between here, like the zippers of a teeth, like the teeth of a zipper. This interdigitation, like the teeth of a zipper, is also going to anchor the cell in place. Right? As well as connecting with these fibers that run across the cell, these microfilaments. That's going to provide a wire running through the entire strip of epithelium that's providing this tensile strength. It's not only are we preventing movement at the surfaces, but these wires run throughout the length of each cell and anchoring the entire epithelium in place. That gives the epithelium some integrity against stretch. So if you try to stretch this epithelium, it was not going to go anywhere because of the desmosomes. So these two are essentially keeping everything in place. This is preventing movement of molecules in between. This is providing a tight seal. And lastly, we have the gap junctions. The gap junctions are way down at the bottom. The gap junctions are way at the bottom. And these are essentially for communication between cell to cell. So we do want these cells to have some synchronicity between them. So they are able to communicate via these tiny little channels. So this is like a hollow little tube provided by a protein called an annexon. So this tiny protein is called an annexon. It's inserted into the membrane of both cells, and it provides like a little channel with this cell is going to talk to the other cell. You can communicate with the cell. And that's your gap junction. This is going to be very important in cardiac myocytes. Cardiac myocytes need to have synchronicity. The entire muscle needs to be beating. That's the conduction system of the heart. You don't want one myocyte contracting and one not. So they need to have a way to speak to each other. And they do so through gap junctions. So those are the four junctions that are found in the lateral surface of epithelial cells. All right, now we'll move on to the basal surface of the cell. So the basal surface of the cell is basically resting on what's called the basement membrane. The basement membrane. And the basement membrane is made of two things. It's made of a basal lamina, and the basal lamina is a sheath that runs across, right? And it's essentially going to help to generate new cells. So if you damage the epithelia and you damage the basal lamina, you cannot regenerate new cells. If you damage the epithelia and keep the basal lamina intact, you can provide new cells. It's going to help with the generation of cells. It's also going to help with scaffolding. So providing some stacking or some integrity under it. You don't just have the cell sitting on connective tissue. It's going to help stack or scaffold this epithelia so it's nice and structurally supported. We also have the reticular fibers. Now, the reticular fibers are from underlying connective tissue. So they're actually the fibers that come from the loose connective tissue that's underneath the basal membrane, and they project upward, come in contact with the basal lamina, and essentially keep things nice and stable. They're going to structurally support the integrity of the basal surface of the cell. And so together, the basal lamina, which is that sheath, along with the reticular fibers from the loose connective tissue, basically assure that from the underneath, the basal surface, this epithelia is not going to move, it's structurally supported and anchored to the loose connective tissue. And again, if you damage epithelia and you damage the basal lamina, you essentially damage that tissue permanently. You cannot regenerate new epithelial cells. If the basal lamina is intact, and there are some microbes that actually damage the basal lamina of tissues, and so we lose the integrity of the tissue. We cannot regenerate new tissue. All right, so this is an example that we spoke about here. the basal lamina, this thin strip of tissue here. Basal lamina, this is the basal surface of the epithelial cell. The basal surface of the epithelial cell. This thin strip is the basal lamina. And then these fibers, and this is the loose connective tissue underneath, that's providing blood and nutrients to the basal surface of the cell. Right? This tissue underneath has fibers in it. These are called reticular fibers. And these fibers are going to extend upward, come in contact with the basal lamina, and together, those two structures are the basement membrane. Now remember, these cells do not actively receive blood supply. What happens is nutrients diffuse from this blood vessel in the underlying connective tissue to feed these cells. They do not get direct blood supply. Remember, we said that they are avascular, but they are innervated, so the nerves do extend out. Any question?
So on the picture, it says the reticular fibers is right underneath the basal lamina.
Right.
But do the fibers contain all like the little swigglies around the vessel too?
Yeah, these are all fibers within that basal lamina. So they're connected essentially. They're not two structures like this. They're connected. But I just want to point out that the fibers are not a part of this structure. Essentially, they're coming from, they're just reaching up, if that makes sense. Does that make sense, everyone? Reticular fibers are originating from the underlying connective tissue. That's where they're coming from. But they are reaching up, coming in contact with the basal lamina to, again, anchor this tissue to the underlying connective tissue, because you want to keep it anchored. Okay, does that make sense? All right, so we're going to talk about apical surface features. So there are two important modifications or features of the apical side of the cell. Those are microvilli and cilia. Microvilli are the finger-like extensions of the plasma membrane. And when I say finger-like, I mean they're going to go up and down, right? And this increases surface area. This increases surface area. So if you were to stretch that membrane out, because you have that up and down, this finger-like projection, you have more surface area to absorb nutrients. That's why if you stretch out the intestines, you can cover something like a football field. Because those interlubrications that increase surface area. And then we find the kidney tubules and the small intestines, areas where we want to increase surface area for absorption, specifically the small intestines. And then cilia is going to be found in the respiratory area, as we mentioned, to sweep that mucus along, as well as the uterine tubes and parts of the uterus to sweep the ovum or the fertilized egg along. Okay, cilia. And the word cilia actually comes from the Latin word which means eyelash. And if you think of the movements of cilia as like the beating of eyelashes, that can help you remember its function, that motility. And so the microvilli do not move, and they're not as tall and as wispy as cilia. The cilia are motile, and their job is to sweep or propel mucus in the case of the respiratory tract, and the ovum in the case of the uterine tubes along the surface of the epithelium.